Mars seems like the obvious next world, but that only works if the goal is sending humans there, if the real goal is finding life. Europa starts looking much more dangerous, because Mars may preserve a dead past, while Europa may still have a living ocean under its ice, and once that clicks, the whole debate changes. A Martian day lasts 24.6 hours, so it is close enough to an Earth day that human routines could adapt to it. Gravity is about 38% of Earth's gravity, which is harsh but still within a range people can picture living with. Mars is about half Earth's size, but because Earth has oceans covering most of its surface, Mars still has roughly the same amount of land area as Earth. And then there is everything else that makes Mars feel familiar. It has weather, it has seasons, it has clouds, it has polar caps. It has the biggest volcano in the solar system. It has canyons so large they make Earth's look small. Mars looks like a damaged world, but still a world. You can picture a rover there. You can picture a habitat there. You can picture a person standing there. That matters, because the easier a place is to picture, the easier it is to treat it as the correct answer before the science even starts. Now ask the same question with Europa, and the emotional picture falls apart immediately. Europa does not feel like a place where humans would build a base. It is one of Jupiter's moons, and it sits inside a brutal radiation environment. It is about 671,000 kilometers from Jupiter, around 417,000 miles. It is only about 3,100 kilometers across, about 1,940 miles, which makes it around 90% the size of our moon. It is covered in ice. The surface is not the part scientists care about most. The thing that matters may be buried under an ice shell that could be about 15 to 25 kilometers thick, around 10 to 15 miles. So the moment you say Europa instead of Mars, you are not just comparing two destinations, you're comparing two completely different reasons to explore space. Mars fit the human frontier story. Europa does not. Europa forces a harder question. Are you exploring to settle, to expand, to build, to compete, or to search for life? That is why you cannot answer this honestly until you choose your metric first. If your metric is where humans could live first, Mars wins so hard that the debate is almost over. Mars gives you a surface you can land on, drive across, drill into, and maybe someday build on. Europa gives you ice, radiation, dim sunlight, and a target hidden below the surface. But if your metric is where alien life is more likely to exist right now, then the conversation swings hard toward Europa. Mars gives you access, but Europa may give you better odds. Mars is easier to reach scientifically. Europa may be more valuable biologically. One world is accessible but probably dead on the surface. The other is inaccessible but may still have a habitable ocean underneath. That is not a minor difference, that is the whole argument. And this is where Mars becomes more complicated than people usually admit. The strongest Mars case today is not really that Mars is alive now. The strongest Mars case is that Mars used to be much better. Mars keeps showing us signs of a more promising past. NASA's Perseverance rover is working in Jezero Crater because that place was once an ancient lake and delta system. That means flowing water entered a standing body of water, dropped sediment, and built exactly the kind of environment that can trap and preserve traces of past biology. Curiosity has also found organic molecules preserved in ancient Martian rocks. None of that proves life existed there, but it does tell you Mars had water, chemistry, and environments that look far more favourable in the past than the Mars we see today. That is why Mars remains one of the most important worlds in planetary science. It may preserve a record of a planet that once crossed into habitability and then lost it. But notice the tense. That is a past tense argument unless something changes. Europa is dangerous in a different way because its appeal is not mainly about fossils or ancient records. Europa is interesting because it may be habitable in the present. That makes it a much more radical target. The big reason is the ocean. Europa may hide a global saltwater ocean beneath its ice shell, and that ocean may contain more water than all of Earth's oceans combined, possibly around twice as much. That should completely reset how you think about scale. Europa looks small if you only look at its diameter. It looks enormous if you think about liquid water. And in astrobiology, liquid water changes everything. Scientists take this seriously because the evidence for that buried ocean is not just speculation anymore. Magnetic measurements from the Galileo mission strongly suggested there is a conductive layer under Europa's surface, and the best explanation is a salty global ocean. That is a major reason NASA built Europa Clipper, because this is no longer just an interesting idea, it is now a serious scientific target. That leads to the real hook underneath the entire debate. Mars may preserve ancient clues about whether life once had a chance on a rocky world that became colder, drier, and thinner over time. Europa may still be running the experiment now under its ice. Mars is a story about past habitability unless new evidence changes the picture. Europa is a story about present-day habitability, and that is a much more volatile claim. Because if Europa has liquid water now, energy now, and the right chemistry now, then the question is no longer whether life once had a chance there. The question becomes whether a living system could still exist in that ocean today. And once you say it that clearly, the whole conversation stops being simple. Mars is still the obvious next world only if your goal is a human future off Earth. But if your goal is to find the most serious nearby place to test whether life exists beyond Earth right now, Mars stops looking automatic. It still matters. It still deserves enormous attention. But it no longer owns the conversation by default. Europa forces its way in because it changes the standard. Mars gives you a place to stand. Europa gives you a place to search. Mars fits the human story more easily. Europa may fit the life question better. So before you choose a world, you have to choose the question. Are you asking where humans can go first? Or are you asking where biology is more likely to still be active? Those are not the same question, and treating them like the same question is exactly why this debate gets confused so fast. The next problem is even bigger. If Mars became the king of space dreams, was that because it was truly the best target, or because it was the one we could most easily turn into a civilization story? Mars became the king of space dreams for a reason, and the reason is not just science. It is that Mars passes the first impression test in a way almost no other world does. The second you look at it, it feels survivable in a way Europa never will. Not safe, not easy, but survivable. That difference matters. Mars has a day that lasts 24.6 hours, and that is a huge psychological advantage because it means a human schedule can fit onto it without breaking. You sleep, wake up, work, rest, and repeat on something close to the rhythm your body already knows. Mars has seasons, it has dust storms, it has clouds, it has polar ice caps. Even its danger feels understandable. When people say Mars is close to Earth, they are not just talking about distance, they're talking about familiarity. They are talking about a world that still behaves enough like a planet that humans can imagine living with it instead of just visiting it. And that first impression goes deeper than most people realize. Mars looks like a place where you could build routines. That matters more than people admit in public. Human beings do not plan civilizations on worlds that feel abstract. They plan them on worlds that feel legible. Mars has sunrise and sunset. It has terrain that looks like terrain. It has weather that looks like weather. It has a horizon that still feels like the horizon of a world. Europa does not give you that. Europa gives you ice and radiation and a buried target. Mars gives you the feeling that if your technology got good enough, and if your systems got reliable enough, then maybe you could keep people alive there long enough to do something serious. That emotional reaction is not scientific proof, but it has shaped the entire cultural story of human spaceflight. Then there is the next advantage, and this one is even more important. Mars is the nearest truly planet-sized target for a civilization project. It is not tiny in the way most moons and asteroids are tiny. NASA describes Mars as having about the same land area as Earth, even though its diameter is only about half of Earth's. That means when people think about settlements, industrial zones, pressurized habitats, greenhouses, fuel plants, mining operations, transport networks, and eventually cities, Mars feels large enough to hold all of that without the whole idea sounding ridiculous. You're not trying to survive on a rock the size of a small country. You're trying to adapt to an actual world. That alone makes Mars powerful. Governments can justify it. Engineers can map it. Companies can project onto it. The public can picture it. Once a destination looks big enough for long-term activity, it stops feeling like a stunt and starts feeling like a stage for history. That is one of the biggest reasons Mars became so dominant. It is not just a scientific target, it is a canvas for human ambition. A small moon or an asteroid can be useful, but it does not naturally support the same scale of dream. Mars does. It has room for all the ideas people want to attach to the future. Expansion, self-sufficiency, industry, backup civilization, resource extraction, scientific outposts and permanent presence. Even before the engineering is solved, the image is already strong. And once that image gets into culture, it becomes very hard to dislodge. Mars is where long-term plans can pretend to become realistic, even when the details are still brutal. But Mars did not become central only because of imagination. It also became central because it was the laboratory we could actually return to again and again. That changes everything. We did not choose Mars only because it looked good in posters. We chose it because missions could keep reaching it. Orbiters could map it, landers could touch down on it, rovers could drive across it, helicopters could even fly there once we got bold enough. Weather stations, chemistry labs, drilling systems, cameras, sample caching, all of that became possible on Mars in a way the outer solar system did not allow at the same level of repetition. By now, Mars is not one destination. It is an entire mission ecosystem. And that repetition matters because science builds on itself. Every mission inherits maps, hazard data, atmospheric models, landing lessons, and years of surface experience from the missions before it. That compounding effect is one of Mars's biggest advantages over Europa. A Mars rover does not arrive in ignorance anymore. It arrives with decades of orbital data behind it. Engineers already know how to think about entry, descent, and landing there. Scientists already know how to frame questions there. Communication systems, navigation planning, terrain analysis, and instrument design all benefit from prior work. That means Mars science keeps getting more precise because it is cumulative. Each mission narrows uncertainty instead of starting over. Europa does not yet have that kind of campaign depth. Europa still lives in the stage where basic reconnaissance is a major achievement. Mars lives in the stage where reconnaissance has already happened so many times that the next step can be more focused and more ambitious. And yet the same data that make Mars feel familiar also expose how brutal Mars really is. This is where the romance starts to break. Mars is not Earthlight. It is not a cold Arizona. It is not a rough version of a place humans can just adapt to with better jackets and stronger walls. The atmosphere at the surface is about 95% carbon dioxide, with only trace amounts of oxygen. Surface pressure is around 1% of Earth's sea level pressure. That means if you stood on Mars without protection, the problem would not just be that you could not breathe. The problem is that the environment itself is fundamentally hostile to human biology and to stable liquid water at the surface. Water does not behave there the way people casually assume it does. In many conditions, it either freezes or turns to vapor quickly. The average surface temperature is around -65 degrees Celsius, about -85 degrees Fahrenheit. So the supposedly easier world in this debate is still a freezing near vacuum with dust, radiation, and almost no breathable atmosphere. That matters because it keeps the Mars case honest. Mars is easier than Europa, but easier does not mean easy. Mars is survivable only in the sense that humans can at least start to engineer around its dangers. You can imagine pressure vessels there. You can imagine buried habitats, nuclear power systems, radiation shielding, local resource use, and vehicles moving across the surface. Those are hard problems, but they are coherent problems. Europa gives you a much more severe version of the same conversation, plus deep ice, plus a severe radiation environment, plus a buried target. Mars at least offers a path where the engineering logic makes sense. It is still harsh, but the Harshness is something engineers can attack in a structured way, and this leads to the real reason Mars became king. Mars sits at the overlap of four motives that almost never line up this neatly. Science lines up there, engineering lines up there, national prestige lines up there, human expansion lines up there. That combination is incredibly powerful. Mars gives scientists a planet with ancient water history and preserved geology. It gives engineers a brutal but workable environment for testing serious off-world systems. It gives governments a visible, dramatic target that the public can understand. And it gives people who think about the long future of civilization a place they can point to as the next major step. Europa does not line those motives up in the same way. Europa is mostly science. Very high-value science, but still mostly science. It does not naturally support the same colonization story, the same industrial story, or the same public image of the next human frontier. So when people say Mars is the obvious priority, what they usually mean is not that Mars is automatically the best answer to every space question. What they usually mean is that Mars is the best answer if your goal is to build a future for humans off Earth. That is a very important goal, but it is not the only goal. And it is not the same as asking where life is most likely to surprise us next. Mars became king because it fits the human project. The problem is that the life question may not care about the human project at all. And once you see that split clearly, the next section gets much more serious. Because if Mars rules the future of human expansion, then Europa matters for a different reason entirely. Europa matters because it may be hiding the kind of environment that changes the search for life far more than Mars ever could. Europa looks small right up until you understand what is under the ice. On paper, it does not sound like the kind of place that should dominate the search for life. It is only about 3,100 kilometers across, around 1,940 miles. That makes it much smaller than Mars, is even a little smaller than our own moon. So at first glance, Europa seems minor. It seems like one more icy moon in the outer solar system. But that first impression fails the second you stop thinking about diameter and start thinking about water. NASA's current summary is the part that changes everything. Europa may hold roughly twice as much water as all of Earth's oceans combined. That means a world smaller than our moon may be hiding one of the largest liquid water environments in the solar system. And once that fact lands, Europa stops looking small in any meaningful scientific sense. That is the first big correction people have to make. Mars looks large because you can see its surface and picture yourself moving across it. Europa looks small because the important part is hidden. But in astrobiology, hidden does not mean unimportant. Hidden can mean much bigger than it looks. If Europa really has a global saltwater ocean beneath its crust, then the place most worth studying is not the ice you can see from orbit. It is the ocean you cannot see at all. That changes the whole scale of the argument. Mars gives you exposed geography. Europa may give you a buried ocean world. And if the real question is where life could exist, then a hidden ocean can matter more than a visible desert. That leads straight to the next problem. If Europa is covered in ice, then what exactly are we looking at when we look at Europa? Scientists currently estimate the ice shell may be about 15 to 25 kilometers thick, around 10 to 15 miles. Below that could be an ocean perhaps 60 to 150 kilometers deep, about 40 to 100 miles. That is the part that makes Europa so strange. The thing you can land on is not the thing you actually care about. The visible moon is not the main environment. It is the cover on top of the main environment. On Mars, the surface is the archive. The rocks, deltas, crater walls, and sediments are the evidence. On Europa, the surface is not the archive. It is the barrier. It is the layer you have to read in order to infer what is happening below it. That makes Europa much harder to study, but it also makes it much more important if the goal is to find a place that could still be habitable now. And that is why Europa's ice should not make you think the story is simple. People hear ice and think dead, frozen, inactive, but ice is not the whole story here. The shell is ice, yes, but the shell is not the world. The world may be the ocean under it, and if that ocean is deep, salty and long-lived, then Europa is not just an ice ball. It is a layered system with a surface, a shell, an ocean, and probably a rocky interior below that. That is exactly the kind of structure that gets scientists interested, because habitability is not about whether a place looks friendly from the outside. It is about whether there is long-term liquid water, chemistry and energy somewhere in the system. Europa may have all of that, just not where human instincts expect to find it. Then there is the surface itself, and this is where Europa starts looking even less ordinary. Europa is covered in water ice cut by long reddish-brown fractures, bands, and broken-looking terrain. It does not look smooth and inactive. It looks disturbed. It looks processed. It looks like something has been happening there. And one of the biggest clues is that Europa has relatively few impact craters compared with what you would expect from an ancient inert surface. Scientists estimate much of the surface may be only around 40 to 90 million years old. In planetary terms, that is young, very young, and young surfaces usually mean resurfacing. Something erased the older record, something renewed the top layer. That matters because resurfacing suggests movement, exchange and internal activity. It suggests Europa is not sealed off in the way a dead world would be sealed off. That is where the tension rises. If the surface is being renewed, then renewed by what? On a place like Mars, you can often explain surface history through impacts, erosion, volcanism, ancient water flow, and the thinning of the atmosphere over time. Europa points you toward a different kind of story. Fractures and bands in the ice suggest stress, motion, and internal forces. The young surface suggests material may be moving upward or sideways, or that the shell itself is being reworked over time. And once you start thinking that way, every crack becomes more interesting. Because if the surface is exchanging material with the interior, then the ocean below may not be completely cut off from the outside. That is a huge and good deal. When scientists look for habitability, they care a lot about exchange. Exchange means chemistry can move. Exchange means the surface may carry clues from the ocean. Exchange means the system is active instead of sealed shut. Now add sunlight to the picture, and Europa becomes even stranger. Europa orbits Jupiter at about 5.2 astronomical units from the Sun. That means it is far outside Earth's orbit, and far outside Mars as well. NASA notes that sunlight there is about 25 times weaker than at Earth, and it takes roughly 45 minutes for sunlight to get there. That tells you something basic but very important. Europa is not a place where sunlight dominates the environment the way it does on Earth. It is not even a place where sunlight feels central in the way it still does on Mars. Europa belongs to a different operating regime. The surface is cold and dim because the sun is weak there. So if Europa has a habitable ocean, the main energy source is probably not sunlight coming down from above. It is something happening inside the moon itself, and that brings in the part that makes Europa so scientifically serious. Europa may be heated from the inside by tidal energy. Jupiter's gravity pulls on Europa constantly, and Europa is also affected by orbital interactions with other large moons like Io and Ganymede. That repeated flexing can generate internal heat. It can stress the ice shell. It can help keep the ocean from freezing solid. In other words, Europa may not just be a frozen object sitting far from the sun, it may be an active ocean world powered in large part by gravity. Mars is cold because it is farther from the sun than Earth, and because it lost much of what once made it more habitable. Europa is a different category entirely. It is a dark world whose most important processes may come from internal heating rather than surface sunlight. That is not a small difference. That is a completely different model of where habitable conditions can exist. So at this point, calling Europa frozen Mars would be completely wrong. Europa is not Mars with more ice. Europa is a separate class of habitability. Mars asks whether life could survive, or once survived, on a rocky surface world that became colder, drier and thinner over time. Europa asks whether life could emerge or persist in a deep ocean under kilometers of ice with almost no useful sunlight at the surface. Mars is mainly a desert planet problem. Europa is an ocean world problem. Those are not versions of the same question. They are different questions with different rules, and that is exactly why Europa matters far beyond Jupiter itself. Because if Europa can be habitable, then the number of potentially habitable worlds in the universe may go up fast. A world does not need blue skies, continents, forests, or an Earth-like surface to matter biologically. It may only need liquid water, chemistry, and energy in the right place for long enough. That is why Europa is so disruptive. It tells you that life may not need the kind of planet humans instinctively look for. It may survive in hidden oceans under thick shells of ice on worlds that look unpromising from the outside. If that is true, then the search for life cannot stay locked onto Mars-like planets alone. It has to expand into stranger environments. And once that happens, Europa stops being a side destination in the Jupiter system. It becomes one of the places that could force us to rethink the map of habitability itself. The next question is even more serious. If Europa may hide an ocean, why do scientists take that ocean idea so seriously now instead of treating it as speculation? Why do scientists take Europa's oceans seriously when nobody has drilled through the ice? Because this is not one clue or one dramatic image. It is a chain of evidence that kept getting harder to ignore. The first clues did not even come from a spacecraft. In the early 1970s, telescopic spectroscopy showed that Europa's surface is dominated by water ice. That did not prove an ocean, but it immediately made Europa different from an ordinary rocky moon. Then Voyager flew past Jupiter in 1979 and made the problem much bigger. The images showed a bright, strange surface with long fractures, very few large impact craters, and far less obvious age than scientists expected from an inert, frozen world. If a surface has only a handful of big craters, that usually means something has renewed it. Something erased the older damage. So before Galileo ever arrived, Europa was already turning from an icy moon into a serious question. It looked young, it looked active, and it looked like the visible surface was not telling the whole story. So what changed Europa from a question into a target? Galileo did. That is the real turning point. NASA now treats Galileo as the mission that made the ocean case scientifically serious, and the reason is very simple. During its time in the Jupiter system, Galileo made 12 close flybys of Europa and measured disturbances in Jupiter's magnetic field around the moon. The best explanation was indecon. In plain language, Europa seemed to contain a conductive layer that responded to Jupiter's changing magnetic field, and the most likely conductive layer was not metal, it was salty liquid water. That is why this measurement matters so much. Scientists may have identified a deep global ocean without ever drilling through the ice. It was not a guess based on appearance. It was a physical signal. Europa behaved the way a moon with a buried salty ocean should behave. Once that happened, the conversation changed. Europa was no longer interesting because it looked weird. It was interesting because the data started pointing to a real ocean world. But then the story gets even more tense, because one of the most famous parts of Europa's case is still not fully settled. People often talk about Europa's plumes as if they are confirmed facts. That is too strong. NASA's wording is much more careful, and that caution matters. Observations from Hubble and reanalysis of older Galileo data suggest it is possible that thin plumes of water rise about 160 kilometers or around 100 miles above the surface. On top of that, water vapor was directly detected above Europa in 2019. That is a very important distinction. Water vapor has been detected, but the full plume story is still not closed in the cleanest possible way, and that uncertainty actually makes the science more intense, not less. Because one solid confirmation of a repeatable plume would immediately change mission strategy. It would mean scientists could potentially sample material coming from the moon without drilling through tens of kilometers of ice. It would turn a nearly impossible access problem into a much more manageable sampling problem. So plumes are not just a detail. They are one of the biggest possible shortcuts in all of planetary science. And right now they remain very promising, but not fully locked down. So if the evidence is serious but not complete, what does the Serious Space Agency do next? It sends a mission built to reduce uncertainty. That is why Europa Clipper exists. NASA did not launch Europa Clipper because Europa sounds exciting in headlines. It launched it because the evidence had crossed the threshold where the next step had to be direct, systematic measurement. Europa Clipper launched in October 2024. It carries 9 science instruments plus a gravity experiment that uses the telecommunication system. It's headed toward Jupiter for arrival in 2030, and its flyby campaign of Europa is designed to include 49 close passes as it studies the Moon's interior, ice shell, surface composition, geology, possible plume activity, and overall habitability. That mission design tells you exactly how NASA sees Europa now. This is not a life detection mission in the simple sense. It is a reconnaissance mission for a hidden ocean world. Its job is to answer the questions that come before any bold claim. How deep is the ocean? How thick is the shell? What chemicals are present? How much exchange happens between the surface and the interior? And are there places below the ice that could actually support life? That is not speculative science. That is what a mature scientific response looks like when the evidence is strong enough to justify a flagship-scale campaign. And that is why Europa is not hype anymore. It used to sit in the category of interesting possibility. It is now in the category of major measurement problem. The path is clear. Early observations established water ice. Voyager showed a strange young surface. Galileo provided the magnetic evidence for a buried salty ocean. Hubble and later work added the possibility of plumes and direct evidence of water vapor above the Moon. Juno made a close flyby in September 2022 and returned the closest look at Europa since Galileo, while also adding new measurements of the ice shell and the Moon's environment. Europa Clipper is now on the way. ESA's JUICE mission is also in flight and is expected to arrive at Jupiter in July 2031 as part of a broader effort to study the giant planet and its icy moons. Put all of that together and the message is hard to miss. Europa has moved out of the zone of speculation and into the zone of sustained high-priority investigation. And once that happens, the old assumption that Mars is the only serious nearby life target starts to break down fast. The next question is just as uncomfortable. If Europa's case is getting stronger, does that make Mars look weaker, or does Mars still matter for a completely different reason? So if Europa is getting stronger, does that mean Mars is getting weaker? No, it means Mars is important for a different reason. Mars is not a blank world, it is a damaged one. That is the key to understanding why it still matters so much. When people call Mars barren, that is true in the present, but it misses the bigger point. Mars looks like a world that lost something. Today its atmosphere is very thin, around 1% of Earth's sea level pressure, and it is mostly carbon dioxide. The air is too thin, the surface is too cold, and liquid water is not stable for long in normal surface conditions. But the evidence keeps pointing to a different Mars in the past. A thicker atmosphere, more water, more active surface systems. So Mars is not powerful as a story because it never had a chance. Mars is powerful because it may have had a real chance and then lost it. That makes Mars more than a dead planet. It makes Mars a record of planetary failure, and that is exactly why scientists keep going back to it. That is also why Mars still matters even as Europa rises. Mars gives you a direct way to study what happens when a rocky world crosses toward habitability and then falls away from it. That is not a small scientific question. It is one of the biggest questions in planetary science. If Mars once had a thicker atmosphere, more stable water, and environments that life could tolerate, then the obvious next question is whether life ever started there, and if it did, whether any trace of it survived in the rocks. Mars may not be the best place to look for living biology right now, but it may still be one of the best places to study how habitability can appear and disappear on a planet that once looked far more promising than it does today. That becomes very clear when you look at Jezero Crater. Perseverance did not land there because it looked dramatic from orbit. It landed there because orbital data showed a delta. That means a river once flowed into a standing lake in that crater. And that matters because deltas are exactly the kind of places where water slows down, drops sediment, and traps chemical and possibly biological signals in layered deposits. NASA now describes Jezero as a place that once had a habitable, stable lake delta river system in its history, and later work added evidence that high-energy flooding also affected the area. That combination is important. It tells you Jezero was not shaped by one simple wet event. It records a longer and more complicated water history. Mars is not promising because it has nice scenery. Mars is promising because its rocks record water moving, settling, eroding, depositing, and changing the environment over time. When you want to search for ancient biosignatures, that is exactly the kind of place you target. And Jezero also shows why Mars remains such a strong robotic science destination. The evidence is exposed, the geology is visible, a rover can drive up to an outcrop, drill into it, analyze it, and cache samples for future return. That kind of work is slow, but it is direct. You're not guessing only from a distance. You are touching the archive. You're reading layer after layer of environmental history in the open. That is a huge advantage Mars still has over Europa. If Mars once supported habitable conditions, its sediments may have preserved the evidence in a way scientists can actually reach with current technology. Then there is curiosity, and this is where Mars stays scientifically alive, even when the strongest life argument keeps shifting toward the past. In 2025, NASA announced that Curiosity had detected the largest organic compounds yet found on Mars: decane, undecane, and dodecane, molecules with 10, 11, and 12 carbon atoms. The likely explanation is that they are fragments of preserved fatty acids. That does not prove life. It does not even come close to proving life by itself, but it does matter a lot. Earlier organic detections on Mars were important, but this result showed that more complex organic chemistry can survive in Martian rocks than many people expected. And that changes the level of confidence scientists can have in the planet as a place that preserves chemical history. Every time Mars preserves something a little more complex, the gap gets smaller between interesting chemistry and chemistry that could have supported biology or recorded biology. That is why each new organic detection matters, even when it falls short of a biosignature. Mars also keeps refusing to become fully boring in the atmosphere, and that is another reason scientists do not stop paying attention. Curiosity has contributed to the long-running methane mystery, and it also found puzzling seasonal oxygen behaviour. None of that should be oversold, none of it is proof of life, but it matters because it shows Mars is not fully explained yet. The modern Martian atmosphere is roughly 95% carbon dioxide, about 2.6% nitrogen, and around 1.9% argon, with very small amounts of oxygen and carbon monoxide. On paper that sounds simple. In practice, Mars still produces seasonal and chemical signals that are not perfectly settled. That keeps the planet scientifically active. A world that still has unresolved chemistry is a world where surprises can still happen, even if the best explanation does not end up being biology. That is really the cleanest way to frame Mars now. Mars earns its place, but mostly as a fossil-hunting world. It gives you exposed outcrops, sedimentary layers, deltas, ancient lake beds, chemical clues, organic compounds, and now cached samples that could one day be studied in Earth laboratories. If you want to know whether a rocky planet once crossed into habitability and maybe even biology, Mars is still one of the best places in the solar system to investigate that question. It is accessible enough for repeated missions, it is complex enough to stay interesting, and it preserves its history in ways a rover can actually study. But the tension in this whole debate comes from one simple shift. Mars is extraordinary if your question is about past habitability and ancient life. Europa becomes more dangerous if your question is about present habitability and living systems now. Mars gives you evidence in stone. Europa may give you an active environment. Mars lets you read the record of what may have happened. Europa forces you to ask what may still be happening. That is why Mars has not become irrelevant. It has become more specific. It is no longer just the default life target. It is the place where you read the history of a world that may once have worked. And once you separate those questions, the next section gets sharper. If Mars is strongest as a world of ancient habitability, then Europa's case becomes more radical for one reason. It may still have the ingredients for habitability operating right now, so what makes Europa more radical than Mars? It is not just that Europa might have water, It is that Europa might have the full set of conditions that matter for habitability operating right now, and the first part is the most important one: liquid water. In astrobiology, water matters because it is the medium that lets chemistry move, react, combine, separate, and keep going over long periods of time. Water is where molecules meet, where gradients can form, and where complex chemistry has room to continue instead of stopping immediately. Mars clearly had water in the past, lakes, rivers, maybe even larger bodies of water. But Europa may have something much more powerful for the life question. It may have a global salty ocean beneath the surface today, and that ocean may contain roughly twice as much water as all of Earth's oceans combined. That is the kind of fact that changes the tone of the whole debate. Mars gives you a better past. Europa may give you a present that never fully shut down. And that difference matters more than people think. When you compare worlds for life, long-term persistence matters more than old evidence that the system used to work. Mars had wet periods and then lost them. Europa may still have a stable liquid environment now. That does not mean life exists there, but it means the basic physical setting may still be available. And that is a huge difference. A world that once had lakes is important. A world that may still have a deep ocean is more dangerous scientifically, because it moves the question from history to current conditions. You are no longer asking only whether life could have started in the past. You are asking whether a habitable environment may still be active in the present. But water alone is not enough, and this is where Europa gets even stronger. Habitability is not just about having liquid somewhere, it is about what that liquid is doing chemically. Europa's case is not simply that there is an ocean. The case is that the ocean may be part of a system that includes chemistry from multiple sources. The icy shell may contribute oxidants and other surface-produced materials. The rocky interior may contribute minerals and chemically useful compounds from below. Surface materials appear to include salts and sulfur compounds that have been altered by radiation. And if those materials can move downward, while ocean material moves upward, then you have exchange. That is the word that matters. Exchange means the ocean is not isolated in a chemically dead way. It means materials, gradients, and reactants may move through the system over time. That is the kind of detail that turns Europa from interesting to serious. A puddle is not enough. A trapped pool of water with no long-term chemical cycling is not enough. Habitability depends on sustained processes. You need a system that can keep generating usable chemistry instead of just sitting there. Europa increasingly looks like that kind of system. The rocky seafloor could chemically feed the ocean from below. The ice shell and surface environment could alter or deliver materials from above. Radiation at the surface is destructive, but it also drives chemistry that may become important if any of it gets transported downward. So the real picture is not just ocean under ice. The real picture is a layered world where chemistry may be moving between compartments. That is a much more serious habitability case than just saying there is water somewhere in the dark. Then the argument gets even harder to ignore, because Europa may not just have water and chemistry, it may also have a long-term energy source, and that is where the whole thing becomes much more radical than Mars. Europa is constantly flexed by Jupiter's gravity, and that effect is reinforced by orbital resonance with Io and Ganymede. In simple terms, Europa is being pulled and squeezed over and over again. That flexing generates heat inside the moon. It likely helps fracture the ice shell, and it may also drive activity deeper down, possibly even volcanic or hydrothermal activity on the seafloor. And that is a major point, because once you start talking about hydrothermal environments, you are talking about one of the most important analogues for life that does not depend on sunlight. That changes the question completely. The Europa question is no longer just, is there water under the ice? The better question is, could that ocean have water, chemistry, and usable energy at the same time for long enough to matter biologically? That is a much more serious question, and it is why Europa has become one of the strongest present-day habitability candidates anywhere near Earth. On Mars, the most persuasive argument points backward. Ancient water, ancient lakes, ancient habitable settings. On Europa, the strongest argument points to conditions that may exist now. Liquid water now. Chemical exchange now. Energy from tidal flexing now. That word now changes the stakes of the entire comparison. And that is exactly why Europa is so important. You're not just reconstructing a dead environment from old rocks. You're asking whether a living environment can exist on a world that looks completely hostile from the outside. No blue skies, no rivers on the surface, no forests, no continents, almost no useful sunlight at the top. If a place like that can still support habitability, then the map of possible life in the universe changes fast. It means Earth-like surfaces may not be the main standard we should be using. It means worlds that look dead from the outside may still hide active environments below. It means the habitable universe could be much larger and much stranger than the Mars First story suggests. That is why Europa is more philosophically disruptive than Mars. Mars still fits a familiar template. It has weather, landforms, ancient rivers, and a thin atmosphere. Even when it is harsh, it still feels like a damaged surface world. Europa does not fit that template at all. Europa says life might not need a normal surface world. It might not need open oceans under the sky. It might not need continents or rainfall or sunlight reaching the place where biology actually operates. It might survive in hidden oceans under thick ice, powered by tides and rock-water chemistry. And if that is true, then many more worlds become interesting very quickly. So Europa is not just another destination in the solar system. It is a test of a much bigger idea. If Europa is habitable, then habitability is not limited to places that look vaguely Earth-like. It can exist in dark subsurface oceans on icy worlds far from the sun. That would not just add one more place to search for life. It would force a broader rewrite of where life could exist at all. The next step in the debate is where it gets uncomfortable. If Mars is better for ancient life and Europa is stronger for present-day habitability, then which one is actually better if your goal is not just to find conditions for life, but to find life itself? So where would you actually go if the goal was not just to study habitability, but to find life? That sounds like one question, but it is really two different questions hiding inside each other. Are you trying to find evidence that life existed in the past? Or are you trying to find a place where life could still be active now? The answer changes depending on which one you mean, and that is exactly where Mars and Europa split apart. Mars is the better place to search for ancient life because Mars gives you the kind of evidence that can stay in place for a very long time. Rock layers, sedimentary deposits, crater walls, ancient deltas, dry lake beds, exposed minerals. All of that matters because ancient biology does not need to still be alive for you to detect it. If microbes once lived in Martian lakes or wet sediments, their traces could have been trapped in minerals, locked into rock textures, preserved as chemical residues, or buried in deposits that stayed stable for billions of years. That is why Perseverance is caching samples in Jezero. It is not just collecting random rocks, it is collecting pieces of an environment that once had moving water, standing water, sediment transport, and the kind of long-term geological setting where biosignatures have a chance to survive. Mars is still one of the best places in the solar system to search for the remains of biology, because the record is out in the open, and in some places, it may have stayed relatively still. That is one of the biggest reasons Mars remains so strong scientifically. Ancient life leaves behind a different kind of target than living life. You do not need a functioning ecosystem, you need a preserved record. Mars gives you exactly that kind of problem. The evidence, if it exists, may be mineralized, entombed, and waiting in rocks that can be drilled, imaged, and eventually studied in much more detail back on Earth. That makes Mars a very strong place to investigate whether a rocky planet ever crossed the line into biology, even if that biology died a very long time ago. Europa flips the entire problem. If life exists there, the strongest version of that claim is not that life used to exist and left traces behind. It is that life could still be there now. That is what makes Europa more exciting and also much harder. If there is biology in Europa's ocean, then the target is not sitting still in exposed rock on the surface. It may be buried under many kilometers of ice. It may be suspended in an ocean you cannot directly reach. It may only reveal itself through chemistry, particles, or materials that somehow move from the ocean to the shell or from the shell to space. So Europa is not just a harder version of Mars, it is a different kind of search entirely. The possible payoff is bigger because active life would be far more important than ancient traces. But the engineering problem is much worse because the environment you care about is hidden. That is why Europa is higher reward and higher difficulty at the same time. If Mars gives you the better preserved archive, Europa may give you the better chance at an active system. But the active system is locked away, and that creates a brutal trade-off. On Mars, the evidence may be older but easier to access. On Europa, the evidence may be more current but much harder to reach. That is the real structure of this debate. It is not simple versus complex. It is accessible past versus inaccessible present. The biosignatures are different too, and that tells you just how separate these two searches really are. On Mars, you're usually looking for signs tied to field geology. You look for textures in sedimentary rocks, mineral patterns linked to water, organic residues preserved in ancient layers, and chemical signatures that make more sense in a wet, habitable environment than in a dry, sterile one. The strategy is to read rocks, compare layers, reconstruct environments, and then eventually bring the best samples home for lab analysis. Mars is a geology-first life search. The surface itself is the evidence field. Europa forces a very different strategy. There, you are more likely to look for ocean-derived salts, organic compounds if any are transported upward, particles from plumes if plumes are real and accessible, redox gradients, and signs that surface materials and deep interior chemistry are interacting over time. On Mars, you often ask what this rock says about a vanished environment. On Europa, you ask whether chemistry from a hidden ocean is reaching places where you can measure it. Mars is mainly a field geology problem. Europa is much more a geophysics and ocean chemistry problem. Even if both worlds are part of the same broad search for life, the actual work is different at almost every level. And that is why the phrase "best place to search for life" is too vague to be useful. It sounds clean, but it hides two separate goals. Where are you most likely to detect past biology? And where are you most likely to find a currently habitable system that could still support life now? Mars may still be the stronger answer to the first question. Europa may already be the stronger answer to the second. Once you split the problem that way, the old Mars versus Europa argument starts to fall apart. They are not really competing for the exact same prize, they are leading in two different categories. That is also why this debate starts to become uncomfortable. For a long time, the public story about the search for life in the solar system got attached almost completely to Mars. Mars was the place, Mars was the main symbol, Mars was where people assumed the life question would be settled. But the more we learn, the less simple that looks. Mars keeps showing us ancient lakes, deltas, organics, and a planet that was more habitable long ago than it is now. Europa keeps pointing toward a buried ocean, chemical exchange, tidal energy, and a world that may still have the key conditions operating in the present. So the centre of gravity starts moving, not away from Mars entirely, but outward toward a more difficult and possibly more important target. That does not make Mars less valuable. It makes Mars more specific. Mars may be the better record of whether life once got started on a rocky planet and then vanished. Europa may be the better test of whether a hidden ocean world can support a living system right now. Mars gives you testimony from the past. Europa may give you a current environment still worth testing in the present. And once that difference becomes clear, the phrase instead of Mars stops sounding like a strange provocation. It starts sounding like a serious scientific question. The next problem is just as sharp. Even if Europa looks more promising for living systems, can we actually study it properly? Because a better target does not help much if the target is buried under ice and locked behind an engineering problem we are nowhere near solving directly. So what is the catch? The catch is that Europa may be the more exciting target for present-day habitability, but Mars is much easier to study in a serious, repeatable way. That difference is not small. It controls the whole pace of discovery. On Mars, you land and the science starts almost immediately. A rover touches down, unfolds, checks itself, and then begins moving across exposed geology. The surface is where the story is written, and it is also where you can work. You can drill into rock, analyze dust, sniff the atmosphere, image layered sediments, cache a sample core, or watch weather happen in real time. You do not first need to get through a massive barrier just to reach the environment that matters. That is why Mars science compounds so well. The evidence is out in the open. It may be incomplete, and it may be ancient, but it is accessible. That accessibility changes everything. It is why Mars can support long campaigns instead of one dramatic attempt. Every successful mission adds more maps, more landing knowledge, more environmental data, more surface context, and more confidence for the next mission. Mars lets you build a scientific rhythm. You're not solving the hardest problem before you can even begin. You can start with the surface because the surface itself is the archive. That is a huge advantage when your goal is to build a layered understanding over time. Europa is almost the exact opposite. The main target is hidden under an ice shell that may be around 15 to 25 kilometers thick, roughly 10 to 15 miles. That single fact dominates the entire mission problem. The thing you want most is underneath the thing you can reach first. So any simple slogan about going to Europa runs into the same question immediately. Go there and do what? Orbit and map it? Fly through a plume if one exists? Land and analyze the surface? Use radar to probe downward? All of those are real steps, but none of them are the same as directly reaching the ocean. A true ocean access mission would mean drilling or melting through kilometers of alien ice in one of the harshest environments in the solar system, while keeping the system sterile enough to avoid contaminating the target and robust enough to keep operating far from Earth. That is not just a hard mission. That belongs to a completely different level of engineering from anything we've done on another world. And that is why plume science matters so much. If Europa really vents material from the interior into space, even occasionally, the whole exploration problem changes. You're no longer limited to the idea of cutting through the entire ice shell before learning anything meaningful about the ocean below. Instead, you may be able to sample the ocean's chemical fingerprints in space or on the surface, especially if some of that material lands in relatively fresh deposits. That is why the current plume evidence is so important, even though it is not fully settled. If plumes are real, repeatable, and connected to the ocean, or to pockets within the shell that still reflect the internal environment, then Europa becomes far more reachable scientifically than it first appears. One clean, confirmed plume would be a major shortcut. It would let scientists investigate possible interior material without solving the full-bore problem of direct ocean access. That is also why Europa Clipper is designed the way it is. It is not a lander. It is not a drill mission. It is a reconnaissance mission, built around the reality that Europa is promising but locked. Its job is to find out how locked. The magnetometer and plasma instruments refine the ocean case and the moon's interaction with its environment. Radar probes the shell to look at its structure. Gravity measurements help reveal the moon's internal arrangement. Ultraviolet and infrared instruments search for plume activity and map surface composition. In other words, Clipper is not trying to do the final act first. It is trying to answer the questions that come before the final act. How thick is the shell? How does material move? Are there active regions? Are there places where fresh chemistry reaches the surface? Does the lock have cracks? That is the only serious way to approach Europa at this stage. Not by pretending the ocean is already in reach, but by scouting carefully enough to learn whether reaching it can become realistic later. On Mars, a rover can begin doing first-rate science soon after landing. On Europa, the first serious step is to reduce uncertainty about the environment before anyone even pretends a direct access mission is near. That is why Europa's science feels slower and more indirect. The world is not giving up its answers easily. You have to infer, map, measure, and narrow the problem piece by piece. So the paradox here is very clean. Mars is easier and less biologically exciting in the present. Europa is harder and potentially much more biologically exciting in the present. That is why this question keeps coming back. If your standard is engineering practicality, Mars wins. If your standard is the possible payoff from one clear sign of present-day habitability, Europa becomes much harder to ignore. The better science target is not always the easier science target. In fact, it usually is not. And Europa may be one of the clearest examples of that in the entire solar system. The next problem makes Europa even tougher. Even if you can measure the surface and maybe sample fresh material, Jupiter's radiation environment keeps damaging that surface, changing the chemistry, and making both science and exploration much harder than they would be on Mars. So what makes Europa even harder than the ice problem? Radiation. Europa is not just cold, it is being bombarded all the time. The Moon sits deep inside Jupiter's radiation environment, and that changes almost everything about how you explore it and how you interpret what you find. This is one of the most important differences between Mars and Europa. On Mars, the surface is exposed and hostile, but it is still a place where rocks can preserve a readable history. On Europa, the surface is being constantly processed by energetic particles. That means the top layer is not just a frozen record. It is an active chemical damage zone. So even if material from the ocean or the deeper ice ever makes it to the surface, you cannot assume it arrives there clean and stays there clean. The surface is not a simple sample tray. It is a place where molecules can be altered, broken apart, or changed after they arrive. That changes the question immediately. On Europa, the question is not only what reached the surface, the question is also when did it reach the surface, how long has it been sitting there, and how much of it has been chemically changed since then. That is a much harder problem than people usually realise. If scientists detect salts, sulfur compounds, or organics near the surface, they still have to ask whether those materials reflect the ocean below, the shell above, or some combination that has already been changed by radiation. In other words, the chemistry may be real and important, but it may also be edited. The longer a sample sits near the surface, the less straightforward it becomes as evidence for the interior, and that means freshness becomes a scientific variable. On Mars, exposed rocks also get weathered, oxidized and irradiated over time, but Europa is a more extreme case because the radiation is tied directly to Jupiter's powerful radiation belts. That makes location matter in a much more serious way. Where you sample on Europa is not just about geological interest. It is also about whether the chemistry there is still close enough to its original state to mean what you think it means. A fresher deposit may tell you much more than an older one. A recently exposed fracture may be more valuable than a surface that has been processed for a long time. A region with lower radiation exposure may preserve information better than a region that has been more heavily bombarded. So on Europa, site selection is not just a technical detail, it is part of the scientific logic itself. That is one reason Europa's surface is both exciting and frustrating. The reddish streaks and disrupted terrains are interesting because they may reflect salts and other materials that came from below or were altered by exchange between the interior and the surface. But those same materials may already have been modified by radiation after they got there. So the visible chemistry can be important and misleading at the same time. The surface may carry clues to the ocean, but the clues may not be in their original form. That is why scientists have to be careful. A colour pattern or a spectral signal may look dramatic, but it is not automatically a clean window into the ocean below. Europa does not give simple answers. It gives signals that may be meaningful but require a lot of interpretation. That is also why Europa is such a difficult place for biosignature work. Radiation is bad for people, bad for electronics, and bad for fragile chemical evidence. On the human side, this is one of the biggest reasons Europa is nowhere near the same category as Mars for future astronauts. Mars is dangerous, but Europa's radiation environment is a much more severe operational problem. Keeping people alive there would be an entirely different level of challenge. But even if you ignore human missions and focus only on robots, radiation still matters because it can actively damage the very organic traces you might want to detect. A surface sample on Europa may be important, but it may also be partly destroyed by the time you reach it. So radiation is not some side issue, it is a direct limit on how clean your science can be. And this is where Mars has an underrated advantage that often gets overlooked. Mars may be less biologically promising in the present, but Mars is often easier to interpret. If you drill into a sedimentary rock in an ancient delta on Mars and run chemistry on it, you are still dealing with a hostile environment, but you're not dealing with the same level of constant Jovian surface reprocessing. That matters a lot. Discovery is not only about where life is more likely, it is also about where your evidence is more likely to be understandable and convincing. A place can be very exciting and still be hard to read. Europa may have the more important active environment. Mars may still give you cleaner evidence when you actually measure something. That creates another uncomfortable split in this whole debate. Europa may be the better place to chase present-day habitability, but Mars may often be the better place to make a case that other scientists will trust quickly. On Europa, every result has to be filtered through questions about radiation damage, freshness, surface processing, and whether the chemistry has been altered after exposure. On Mars, the environment can still confuse you, but often in a less severe way. That makes Mars more conservative scientifically, but also clearer. Europa may be more exciting, but excitement is not the same thing as interpretability. So radiation changes the meaning of almost every measurement you might want to make on Europa. It affects where you go, what you collect, how you read the data, how long a surface clue remains useful, and how much confidence you can have that a signal still reflects the ocean below. That is why Europa is not just a harder Mars. It is a world where the environment keeps rewriting the evidence even after the evidence reaches the surface. And once radiation enters the picture, the next section gets even more practical. Mars is already difficult, but Europa is not just farther away. It belongs to a much more remote, slower, colder, and more energy-starved mission regime. So how much harder is Europa than Mars in pure mission terms? Much harder. Mars is distant, but Jupiter is remote in a completely different way. Mars orbits at about 1.5 astronomical units from the Sun, with an average solar distance of roughly 228 million kilometers, about 142 million miles. Jupiter is out at about 5.2 astronomical units, around 778 million kilometers, about 484 million miles from the Sun. That is not just a bigger number on a chart. It means you are operating in a very different environment from the start. Sunlight takes about 13 minutes to reach Mars, takes about 43 minutes to reach Jupiter, so Europa is not just farther away in the simple sense. It sits in a dimmer, slower, colder, more energy-starved regime, where every mission choice gets harder before the science even begins. That matters because when you design a Mars mission, you are still working in a part of the solar system where repeated access is possible. Difficult, expensive, risky, yes, but possible often enough that you can build experience. When you design a Europa mission, you are planning for a place where distance itself changes the whole architecture. Your travel time stretches out, your power situation gets worse, your communications delay gets longer, your thermal control becomes more demanding, your failure margin gets thinner. That is why Europa missions do not just feel bigger, they are bigger in every practical sense that matters. You can see that clearly in Europa Clipper's journey. It launched in October 2024, but it does not just fly straight to Jupiter and arrive a little later. It is on a roughly 2.9 billion kilometer journey, about 1.8 billion miles, to reach the Jovian system in 2030. That alone tells you how different this mission class is. And even that trip is not a straight sprint. NASA used a Mars gravity assist in February 2025 and plans an Earth gravity assist in December 2026 because sending a spacecraft of this scale to Jupiter efficiently means you do not simply point and fire unless you are willing to spend much more propellant. Clipper is around 6,000 kilograms, and getting a machine like that out to Europa's neighborhood is not like running a long Mars cruise. It is a carefully staged orbital campaign. At one point during its Mars flyby, Clipper, approached at about 24.5 kilometers per second, around 15.2 miles per second. That is roughly 88,000 kilometers per hour, or about 55,000 miles per hour. At those speeds, this is not just travel, it is trajectory management at a very high level. And that difference matters because it changes how often you can afford to do this kind of science. Mars missions can fail and still be followed by more Mars missions in a reasonable time frame. Europa missions are major campaigns. They tie up years of planning, long cruise phases, complex navigation, and a level of mission design that is much harder to repeat casually. That is one reason Mars became the place where science could build a cadence, while Europa remained the place of rarer, more strategic attempts. Mars is not easy, but Europa forces you to commit at a much higher level before you even know that if your best assumptions are right. Then there is the power problem, and this one gets ugly fast as you move outward. At Europa's distance, satellite is far weaker than it is near Earth. A simple way to think about it is this. By the time you get out to Jupiter, sunlight is about 25 times fainter than at Earth. Mars, at 1.5 astronomical units, still gets much more workable solar energy than the Jovian system. That difference affects everything. It affects spacecraft power, it affects heaters, it affects communications margins, it affects what instruments you can run and for how long. It affects what kind of lander you might someday build. Mars is still cold and difficult, but it is not operating under the same kind of energy starvation. At Europa, every what matters more. Every instrument becomes more expensive in the engineering sense. Every choice about power is tighter, and once power gets worse, your systems become less forgiving. On Mars, solar power can still be a serious option for some kinds of missions, even though dust and seasons complicate it. Near Jupiter, the environment pushes you into a different class of design thinking. You're not just trying to survive cold and distance, you're trying to survive cold and distance with much less sunlight, while also managing radiation and long communication delays. That makes Europa a place where mission design becomes more constrained from the beginning. You do not have as much margin to waste, you do not get to be sloppy. Communication changes the philosophy too. People often talk about light time delay with Mars as if that already defines robotic exploration. And yes, Mars delay matters. But Jupiter pushes that problem into a more serious category. The farther you go, the less you can rely on quick command response loops from Earth. When something starts going wrong, you are dealing with a longer gap between what happened, when you find out, and when you can respond. That means Europa missions need more autonomy, more fault protection, and more ability to survive problems without immediate help. The spacecraft has to make more decisions, or at least protect itself longer, without waiting for humans to step in. That sounds technical, but it changes the whole culture of mission design. A Europa mission is not just a Mars mission with a bigger fuel bill. It is different in how it has to think, wait, recover, and prioritize. At Mars, you can build a style of exploration around relatively frequent missions and accumulated experience. At Europa, you build around uncertainty, patience, and fewer chances to get things wrong. Outer solar system missions demand a kind of discipline that is different from inner solar system campaigns. The environment forces it, and that is the real reason Mars became routine while Europa did not. Mars missions still fail. Mars still kills spacecraft. None of this is easy. But Mars has become a reachable neighbourhood in a way Jupiter's system has not. That does not make Mars more scientifically important by default. It makes Mars more operationally repeatable, and repeatability matters a lot in real science. It means more missions, more lessons, more retries, more refined questions, and more chances to build momentum. Europa is not like that. Europa is a strategic expedition. You do not visit Europa the way you visit Mars. You commit to Europa. So when people compare Mars and Europa as if they are just two destinations on the same menu, that misses the real difference. Mars is where you build cadence. Mars is where you learn through repetition. Mars is where a civilization with limited budgets and limited tolerance for failure can keep returning, refining, and improving. Europa is where you spend that accumulated capability on a much stranger and potentially much bigger scientific prize. That is why the comparison never stays simple. Mars is operationally easier, scientifically productive, and repeatable. Europa is slower, harder, more expensive, and much more demanding. But the possible payoff is so high that the question will not go away. And once you understand that, the next section becomes even more revealing. Because the missions themselves already show what the scientific community really thinks. Not what people say in arguments, but what agencies are actually willing to fund, launch, and spend decades pursuing. If you want to know what the scientific community really thinks, do not start with speeches. Start with the missions. Missions cost money, time, support, engineering effort, and years of scientific planning. So when agencies keep returning to a world, that tells you more than any debate does. And right now, the mission picture is very clear. Mars is no longer being treated as one bold bet after another. It is being treated as a layered program. Perseverance is collecting and caching samples. Curiosity is still working on chemistry and atmosphere. Orbiters are still mapping the planet, relaying data and adding context from above. And even though the architecture for Mars sample return is being reworked, the goal itself remains important for a very simple reason. Scientists want actual Martian material in Earth labs. That is a major statement of priority. It means Mars is still important enough that researchers do not want to stop at rover-scale instruments forever. They want to bring the evidence home and test it with the full power of laboratory science. That tells you exactly what Mars means now. Mars is still a core target, especially for reconstructing ancient habitability. The entire mission stack points in the same direction. Read the rocks, understand the climate history, study the atmosphere, cache the best samples, eventually return them. That is not the behaviour of a field that has moved on. That is the behaviour of a field that thinks Mars still has some of the best preserved evidence for whether a rocky world once became habitable and maybe even biological. Mars is not fading out. It is maturing into a more precise scientific project. But now look at Europa, and you see something equally important. Europa has crossed into that same elite category. Europa Clipper is not a side mission, and not a bonus add-on to a Jupiter tour. It is the first mission specifically built for detailed investigation of Europa itself, and its science goal is very sharp. Determine whether there are places below the surface that could support life. That wording matters. NASA is not treating Europa as an exotic object that happens to be interesting. It is treating Europa as a primary astrobiology target. Once a world gets a flagship-scale reconnaissance mission designed around habitability questions, that world has entered the top tier. That is where Europa is now. And Europa's rise is not just a NASA story. Europe's JUICE mission reinforces that this is bigger than one agency or one national program. JUICE is exploring Jupiter and its icy moons, especially Ganymede, but Europa and Callisto are also major parts of the scientific picture. The broader message is the important part. Large space agencies are now treating icy moons as ocean-bearing worlds with real astrobiological importance. By 2026, JUICE is still in interplanetary transfer, with another Earth gravity assist ahead and arrival at Jupiter expected in 2031. That means the global exploration effort is now pushing in the same general direction. Not away from Mars, but outward toward ocean worlds. That shift matters because it shows icy moons are no longer being treated like science fiction concepts, they are being treated like long-term programmatic targets. So what is the actual difference between the Mars mission stack and the Europa mission stack? It is the question each one is trying to answer. Mars missions are now focused on stratigraphy, sample caching, atmospheric behaviour, climate history, and eventually laboratory-grade biosignature testing on returned material. Mars science is trying to read a record. It is trying to reconstruct what happened on a world that seems to have been more habitable in the past than it is now. Europa missions are doing something different. They are trying to verify the structure and chemistry of a hidden ocean world. Ice shell thickness, ocean depth, salinity, plumes, internal structure, chemistry and surface ocean exchange, that is the Europa list. One program is reading a planetary history, the other is checking whether a hidden habitat exists right now. That is a major conceptual split, and it shows that the field no longer treats the search for life as automatically identical with Mars. And that means the missions themselves already answer part of the title question. Should we go to Europa instead of Mars? The answer from the agencies is basically this. Not instead in every sense, but absolutely in addition, and with much more seriousness than before. Mars remains the accessible laboratory for ancient habitability, long surface campaigns, and future human exploration. Europa has become one of the highest value robotic astrobiology targets in the solar system. The launch decisions, the instrument packages, the mission timelines, and the scientific priorities all point the same way. Mars still matters enormously, but Mars no longer has a monopoly on the life question. And once you add humans back into the debate, the balance shifts again. Because for robots, Europa may be one of the most valuable science targets we have, but for people, the comparison changes very fast. Now put humans back into the equation and the answer changes fast. Mars is hostile, but it is still a place humans can realistically imagine working on. That does not mean it is easy. It does not mean it is spoilable. It means the engineering logic exists. Mars has a day that is close to Earth's solid ground, exposed geology, and a thin atmosphere that is not useful for breathing, but is still enough to matter for entry, descent, and some aero-braking. It is a real planet-scale surface where you can picture habitats, vehicles, storage depots, power systems, drilling operations, and long-range movement. That matters. Human exploration is not only about whether a place is interesting, it is about whether you can build a whole chain of operations there and keep it running. Mars fits that logic. You can imagine crews landing, living in pressure habitats, driving long distances, using robots and drills, extracting local resources, and gradually building up more capability over time. None of that is easy, but it is coherent, and that is the key difference. Mars gives you a pathway. A hard pathway, but still a pathway. The environment is brutal, but it behaves in ways engineers can work with. You can plan for dust, cold radiation, weak gravity, thin air, and long-distance logistics. Those are serious problems, but they are problems that fit into a recognizable framework of human operations. Mars looks like the kind of place where people could learn how to live off Earth for real. Not comfortably, not soon, and not cheaply, but in a way that makes practical sense if your long-term goal is to become interplanetary. Europa does not fit that logic at all, not even close. Europa has low gravity, an ice surface over an uncertain structure, extreme cold, very weak sunlight, and a radiation environment that is far worse than what people normally picture when they think about deep space hazards. And the most important target is not on the surface anyway. It is underground, below a thick shell of ice. That means even if you somehow solve the travel problem and the survival problem, you would still arrive at a world where the science target is buried and the surface environment is punishing. The Jovian system is one of the harshest operational settings in the solar system. That is not where you build your first off-world civilization. That is where you send extremely hardened robotic missions to answer a very specific question. That is the cleanest way to say it. Europa is not a settlement candidate. Europa is an expedition-grade science objective. You do not go there first to learn how humans expand into the solar system. You go there with robots because the science may be extraordinary, and because the environment is bad enough that sending people there first would make almost no sense compared with what you could do on Mars. If the human goal is long-term presence, infrastructure, and industrial growth, Europa is the wrong first choice by a huge margin. Mars also connects much more directly to the practical side of future exploration. This is where things like local resource use become important. Mars is one of the few places where people can seriously talk about extracting useful materials, making propellant, building structures from local material, and testing long-duration surface operations that could scale up over time. Even before any real settlement exists, Mars is already part of a broader discussion about how humans might produce fuel, use local resources, build landing zones, make shelters more robust, and reduce dependence on constant resupply from Earth. Europa does not connect to that conversation in the same way. Right now, Europa is not where you test the human future. Europa is where you test one of the biggest scientific questions we have. That is why Mars keeps dominating whenever the conversation shifts from where life might be to where humans learn how to stop being tied to one planet. Those are different goals. Mars supports both science and a human pathway. Europa is overwhelmingly tilted toward robotic science. That is not an insult to Europa. It is exactly what makes Europa so valuable. But it does mean you have to keep the categories separate or the whole debate gets confused, and that is what keeps happening in public. People slide back and forth between robotic science goals and human destiny goals as if they are the same thing. They are not. A robot can justify Europa on pure scientific value. A robot does not care that the surface is brutal, the radiation is intense, and the target is buried. It only cares whether the measurements are worth the mission. A human mission has to justify all of those extra costs and risks, and Europa does not come close to winning that comparison against Mars. If the traveller is robotic, Europa can absolutely be one of the best targets in the solar system. If the traveller is human, Mars is overwhelmingly more plausible as the next major campaign. And this is where the argument splits people very clearly. The colonization crowd will keep choosing Mars, and they will have strong reasons. The astrobiology crowd will keep drifting toward Europa, and they will also have strong reasons. That is why this debate works so well. It is not fake. It is not one side being serious and the other side being confused. The disagreement is real because the goals are real. Mars is the better next world for people. Europa may be the better next world for answering whether a hidden ocean can support life. And once that split is clear, the next section gets even more serious. Because if Europa may contain a habitable ocean right now, then contamination stops being just a technical issue. It becomes an ethical one. Planetary protection sounds like a side rule, until you realise it can decide whether a discovery means anything at all. On Mars, contamination already matters because the evidence you are looking for may be subtle. If Mars preserves traces of ancient biology, those traces are probably not going to be obvious in the way people imagine. You are not expecting a skeleton or a fossil shell sitting in the open. You are looking for chemical patterns, textures in rock, mineral relationships, organic compounds in the right geological setting, and combinations of signals that only make sense when you put the full context together. That kind of evidence is fragile in a scientific sense. Not fragile because it falls apart in your hand, but fragile because it is easy to argue about. If you bring contamination into that picture, you make the argument much worse. Suddenly, every signal can be challenged. Was that organic molecule Martian? Or did it come from Earth? Was that pattern ancient biology? Or was it introduced during collection or handling? On Mars, cleanliness is not paperwork. It is the difference between a real result and years of scientific fighting. That is why sample handling, caching, sealing, transport and return all matter so much. If Perseverance collects an extraordinary sample and that sample is later questioned because of contamination concerns, the scientific damage is huge. Not because the rock becomes useless, but because trust in the interpretation becomes weaker. Ancient biosignatures are often statistical, chemical, and contextual. They do not survive sloppy handling. So even on Mars, where the main target is probably ancient life rather than living life, planetary protection is already central to doing the science properly. But Europa raises the stakes much higher, because Europa may still be habitable now. That changes the whole ethical category. Mars is mainly a fossil hunting problem. Europa may be a present-day habitat problem. If Europa's ocean can support life, then contamination is no longer just about protecting the quality of your data. It becomes about protecting another environment from us. That is a completely different level of responsibility. If you are dealing with a world that might still contain habitable niches, then introducing Earth microbes or Earth chemistry into that system is not just a mistake, it is interference. It means you are not only risking false positives later, you're risking damage to the thing you came to study. That is why Europa has to be approached in stages. First you map, first you model, first you constrain the shell, the chemistry, the exchange pathways, the radiation environment, and the regions that may be freshest or most active. You do reconnaissance before you ever start talking seriously about penetration or deep sampling. A world that may contain a living ocean is not something you rush. The closer a target gets to present-day habitability, the less acceptable crude exploration becomes. That is one of the strongest reasons Europa Clipper is exactly the kind of mission it is. It is a disciplined first move, not an impulsive one. And there is an important mistake people make here. They assume Europa's radiation solves the contamination issue by making the surface hostile enough to sterilize everything. That sounds reasonable at first, but it is too simple. Yes, the surface is heavily processed by radiation. Yes, the uppermost layer is a harsh place. But the real target is not the top layer of exposed ice. The real target is the shell below and the ocean below that. If there are cracks, transport pathways, pockets of brine, or any kind of exchange between the surface and deeper environments, then contamination still matters. A world can be surface hostile and subsurface sensitive at the same time. In fact, Europa may be exactly that kind of world. That is what makes the protection problem so serious. You cannot just point at the radiation and assume the whole moon is effectively self-cleaning. The environment is more complex than that. If materials can move downward, or if future missions ever attempt to melt, drill, or penetrate, then whatever comes with the spacecraft matters. And it matters not only because it could confuse later science, but because it could enter a system that might otherwise have remained isolated for billions of years. That is not a normal exploration problem. That is a problem that sits right at the boundary between science, ethics, and restraint. This is another reason Mars and Europa are not interchangeable life targets. On Mars, planetary protection is mostly about reading an archive carefully. You're trying not to contaminate evidence that may already be faint and difficult to interpret. On Europa, planetary protection may be about something more serious. You may be trying not to contaminate a place that still functions as a habitat. Those are not the same philosophy. Mars asks for careful handling. Europa may demand careful handling plus moral caution. One is about protecting the meaning of evidence. The other may be about protecting both the evidence and the environment itself. And the farther the conversation moves from ancient life to extant life, the more loaded Europa becomes. If the goal is only to study a dead record, then contamination is already important. If the goal is to interact with a potentially living system, then contamination becomes a much more serious kind of failure. You are no longer just worried about ruining your experiment. You are worried about altering the thing you came to understand. That is why the idea of eventually reaching Europa's ocean is so powerful and so dangerous at the same time. The deeper you go, the more you need to be certain that you are not bringing your own biology into someone else's possible habitat. That is why Europa is not just scientifically exciting. It is one of the few places nearby that almost demands a different tone. If there is a habitable ocean there, then Europa is not just another destination on a list of targets. It is one of the rarest types of place we know how to imagine, a nearby world where biology may still have room to operate in the present. You do not approach that casually. You do not reduce it to one more mission opportunity. You treat it with a level of caution that matches the possibility. Because if Europa has been running a habitable system in darkness for billions of years, then the first rule is simple. Do not be the thing that ruins the experiment before you understand it. And that leads straight into the real answer. Once you factor in human goals, life detection, engineering limits, and planetary protection, the question stops being which world is better in some simple absolute sense. The real answer depends on what you think exploration is actually for. So what is the real answer? It depends on what you think exploration is for. That is the part people keep skipping. They act like Mars and Europa are competing for one simple prize, but they're not. The answer changes the moment you change the goal. If exploration is about building a second home for humans, Mars wins. That is the cleanest answer in the whole debate. Mars is the place where human systems engineering can connect to a real world in a way that makes sense. You can plan habitats there, you can plan vehicles there, you can plan storage, power extraction, construction, repair, and long-range surface operations there. The day length is close enough to Earth's to support human routines. The terrain is difficult, but it is still terrain. The scale is large enough to support the idea of a real long-term campaign instead of a tiny outpost clinging to a small object. And most importantly, Mars already has mission heritage behind it. We know how to reach it, map it, land on it, drive on it, and study it. That does not make Mars easy. It makes Mars legible. And if you want a civilization project, legibility matters. You do not start with the strangest possible world. You start with the one that gives you the clearest path from survival to permanence. That is why Mars remains so strong in public imagination and in long-term planning. It is not because Mars is kind, it is because Mars is understandable enough to build around. It looks like the kind of place where human effort can accumulate. One habitat becomes several, one landing zone becomes infrastructure, one mission becomes a network. That is not fantasy in the same way Europa settlement is fantasy. It is still extremely hard, but it follows a coherent engineering logic. But now change the goal. If exploration is for answering the life question, Europa gets serious very quickly. Because now you're not asking, can humans live there? You're asking, where is biology most worth hunting next? And under that standard, the balance shifts. A present-day subsurface ocean with chemical inputs and tidal energy starts to look more important than a cold desert with an extraordinary but ancient water history. Mars may preserve the story of a world that was once more habitable. Europa may still contain a place where habitability is active now. That difference is enormous. One world gives you a record, the other may give you an ongoing system. And if your top priority is the search for life beyond Earth, it becomes harder and harder to argue that the easier target is automatically the better one. That is where the centre of gravity starts to move. Not because Mars stops mattering, but because Europa asks a more dangerous version of the life question. Mars asks whether life may have appeared and vanished. Europa asks whether life might still have somewhere to exist right now. Once you frame it that way, Europa becomes much harder to dismiss. Now change the goal again. If exploration is about engineering prestige, Mars still dominates. Mars gives you repeatable campaign logic. You can launch orbiters, then landers, then rovers, then helicopters, then sample caching missions, and eventually maybe crews. Every step is visible. Every step is understandable to the public. Every step proves something about national and civilizational capability. Mars is where you show that you can do hard things again and again in a way the world can see clearly. That matters in reality because space priorities are never set by science alone. They are set by budgets, institutions, and public meaning. Mars fits that system much better than Europa does. Europa does not produce the same kind of visible campaign story. It is more specialized, more robotic, more delayed, and less easy for the public to read at a glance. A Europa mission can be more scientifically radical and still be less legible. That is one reason Mars keeps winning in public conversation. Europa fits the deeper scientific gamble better. Those are not the same contest. Now push the question to its deepest point. If exploration is for rewriting what life can be, then Europa may matter more than Mars. Mars mostly extends a familiar picture. Ancient rivers, ancient lakes, weather, sediments, fossils maybe, climate collapse. Everything about Mars still fits an Earth-like imagination, even when the world itself is hostile. Europa does not fit that imagination. Europa says life might not need a surface world at all. It might not need open water under a sky. It might not need continents, rainfall, or sunlight reaching the place where biology actually works. It might survive in a hidden ocean beneath thick ice powered by tides and chemistry from rock-water interactions. If that is true, then the meaning goes far beyond one moon. Europa would not just tell us something about Jupiter's system, it would widen the whole map of habitability. It would mean that many more worlds could matter than we used to think. It would mean the universe may support life in darker, stranger, less Earth-like places than our instincts ever preferred. Mars expands the story we already know. Europa could force us to replace that story with a larger one. So there is no honest one-word answer here. Anyone who says Mars, obviously, is flattening the science. Anyone who says Europa, obviously, is flattening the engineering and human side. The real answer is conditional, and that is not a weakness. It is the only way to be precise. If the question is where humans should go first, Mars wins. If the question is where extant life astrobiology may have the higher payoff, Europa becomes the more radical target. If the question is where nations prove visible competence, Mars still dominates. If the question is where one discovery could most force us to rethink life in the universe, Europa may matter more. Once you say that clearly, the whole debate gets cleaner and harder at the same time. Mars is not the automatic answer to every version of exploration. Europa is not the automatic answer either. They win under different definitions of success, and that means the real verdict cannot be delayed anymore. So after all of that, should we actually go to Europa instead of Mars? The honest answer is no, not in every sense. We should not abandon Mars across the board. Mars is still too important for that. It is still the best place for long-duration surface science on another planet. It is still the place where you can land, drive, drill, cache samples, and build mission after mission on top of previous experience. It is still the most realistic first target for eventual human exploration beyond the moon. And it is still one of the best places to study a rocky world that seems to have been more habitable in the past and then lost that state over time. Mars gives you access, continuity, and a path for both science and human operations. That combination is too valuable and too rare to walk away from. And there is another reason Mars cannot be dropped. Mars is where different kinds of ambition still line up. Scientists care about its ancient lakes, deltas, sedimentary rocks, organics, and climate history. Engineers care because it is hard but workable. Space agencies care because it supports visible, repeatable campaigns. Long-term planners care because it is the clearest place where humans might eventually learn how to operate off-Earth for real. So even if Europa is rising fast, Mars still holds the centre of gravity for surface exploration, human relevance, and practical continuity. If the question is whether Mars should stop mattering, the answer is absolutely not. But now comes the sharper answer. If your question is not where humans should build experience, but where alien life is more worth chasing next, then yes, Europa may deserve the stronger push. That is the knife-edge answer in this whole debate. Europa likely has a salty subsurface ocean. That ocean may contain roughly twice as much water as all of Earth's oceans combined. It may have chemistry coming from both the surface and the rocky interior. It may have tidal energy driving long-term activity. It may have the kind of ocean-rock interaction that makes people take habitability seriously. Mars gives you a powerful ancient story. Europa may offer a present-day environment that still works, and if the highest scientific priority is finding the best nearby target for current habitability and maybe even extant life, Europa becomes very hard to ignore. That is why the old hierarchy is starting to crack. For a long time, Mars dominated the public imagination as the place where the life question would be answered. Mars was the obvious place. Mars was the first place people thought of. Mars was the symbol. But the evidence has changed the structure of that story. Mars now looks more clearly like a world of ancient habitability, preserved clues, and fossil hunting potential. Europa looks more clearly like a world of present-day habitability, deep uncertainty, and enormous access costs. That is not a small update. That is a change in the architecture of the search itself. The life question is no longer centered only on exposed deserts and ancient riverbeds. It is now also centered on buried oceans and hidden chemistry. The suspense is moving outward, and that matters because it means the real choice is not between two destinations in any simple travel sense. It is a choice between two different purposes of exploration. Mars is where humanity can rehearse becoming multiplanetary. Mars is where people can test systems, build experience, study a once habitable planet up close, and push toward a future where human presence expands beyond Earth. Europa is different. Europa is where humanity may discover that life never needed the kind of world we always assumed it would need. If Europa is habitable, then the universe becomes broader, darker, and stranger in one step. So the comparison is not just about rockets, distance, or budgets. It is about what kind of answer you want most. If you want the world that best supports a long human campaign, Mars still wins. If you want the world that may do the most to rewrite biology in the universe, Europa may matter more. If you want a place where mission cadence, engineering visibility, and eventual human operations all make sense together, Mars remains the lead target. If you want the place where one good result could most radically change the search for life, Europa becomes the more dangerous destination. That is why there is no honest one-word answer. A clean answer would be easier, but it would also be less true. So should we go to Europa instead of Mars? For colonization, no. For long-term human operations, no. For the first serious off-world civilization project, no. Mars is still the better next world for people. But for the deepest scientific question we know how to ask, are we alone? And what kinds of worlds can actually support life? Europa may be the more radical next move. That does not erase Mars. It sharpens Mars. Mars becomes the place where we study how a habitable world can fail and where humans may learn how to live elsewhere. Europa becomes the place where we test whether life can survive in a hidden ocean under ice, far from the kind of planet humans instinctively trust. And that is the real ending. Mars still tells us where we might live. Europa may tell us what life itself is allowed to be. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.